In this video, we're going to find the value of k that makes a certain function have a relative maximum at x equals -2. Let's jump in. Okay, so here's the problem. Go ahead and pause the video and see if you can work this through. Okay, so if we come back, here is the answer. If you got that right, feel free to skip this video. Otherwise, we'll dive exactly into why this works. So one thing you could do is to just start experimenting on your calculator. Now, this would be pretty inefficient on a TI-84, but it's actually pretty efficient with Desmos if you have a slider like I have here. So basically, you can see that as I change this k value right here in our problem, effectively what I'm trying to do, remember, I'm trying to find the k value that makes it so that I have a relative maximum at x equals -2. So pay special attention to this point right here. If I keep moving this around, actually, if I keep moving this around, you can see that if I make k negative, it seems like there's no relative maximum at all. And then if I come down like this, you can see that I can play around it. Apparently, I don't know, it's hard to see exactly, but it looks like k equals 4 is the answer, which we already know experimentally is the answer. So that's one way to do it, but again, that's not a good way. It's very inefficient. So the question is, how do we figure this out by hand analytically? This problem is tricky for a couple reasons. One is because we have to do things backwards from how we would normally do it. On a normal problem like this, we would just take the derivative of the function, set it equal to 0, find the, or does not exist, find the critical points, and then do one of our tests, the first or second derivative test, to see whether those critical points are relative maxes, relative mins, or neither. In this problem, we need to do basically the same thing. It's just that they've given us the x value that they want the relative maximum at, and we have to reverse engineer which value of k would make that happen. So how do we do that? Basically what we can do, again, you can think about it like this. Our function here is y equals x plus k over x. So as long as k is just a number or a constant, we can actually take the derivative of this thing symbolically. So if I do that, think about what I get. I get y prime is equal to 1, and then think about what this is. Imagine this, and you can also think about this as basically x plus, or I'll say it like this, x plus k times x to the -1, if you want to think of it like that. And if you just use the power rule, hopefully it makes sense that you drop a -1 out front and then subtract by 1 to get x to the -2. So this will be effectively minus k over x squared. So we know that this thing is the derivative. Now, what we want, think about it, we want this function to have a relative maximum when x is equal to -2. What has to be true of the derivative whenever we have a relative maximum or relative minimum? It has to be 0. It could also be undefined, but we'll just deal with the 0 case here first to see if we can make that happen. So basically what we can do here is we can just set this equal to 0, and then we can also set x equal to -2, because remember, we're doing things in reverse now. We want to choose things so that we select the k value that makes this 0 at that spot. And then if you're going to work through this, hopefully you can see that we get what 0 equals 1 minus k over 4. And then you can solve this, k over 4 equals 1. So apparently we get k equals 4. That's how you can solve this problem. Now here, we still need to check whether this is the relative maximum, because they could ask a trick question. Remember, at the beginning of the problem here, one of the options is none of these. So just because we've proved that the derivative is 0 at x equals -2 when k is equal to 4, we haven't actually proved that that slope of 0 causes a relative minimum, or sorry, a relative maximum. It could also cause a relative minimum or a saddle point. Remember, like if we have some function here, let me show a couple of different cases. That would be like a relative minimum, that would be like a saddle point, and that would be a relative maximum. All three of these points have a slope of 0. So just because all we've done at this point was we proved that when k is equal to 4, that will cause a slope of 0 at x equals -2. We haven't proved that that actually translates into a relative maximum. So we should still verify our work here. Now think about it. How would we verify our work? If this is our original function, or the derivative of our original function, I should say, and we've just proved that k is equal to 4, we can basically say y prime is equal to 1 minus 4 over x squared, we can basically set up some sample points. So if I choose, let's say, we already know that x equals -2 would work. I'm basically just creating a sign chart here, by the way. So we know that -2 already causes a slope of 0. We can figure out some other values that would also work. So like if we had -1, well, actually, let's just choose some sample points. That's probably the simplest thing we can do. So we can choose something that's immediately to the left of it, so -3, and we can choose something that's immediately to the right of it. I'll say -1. Now you have to be careful with which values you choose here. Like you could have also chosen 0, or you might, in a normal problem, you'd be able to choose 0. But if we choose x equals 0 here, that's actually a problem because the derivative and also the original function would not exist when x is equal to 0. So that's something you have to pay attention to. Make sure the values that you're choosing as your sample points are not where the derivative or the original function would not exist. So if we check this, we can basically plug in -3 for this. So what's 1 minus 4 divided by -3 squared? -3 squared, remember, is 9. 1 minus 4/9 is 5/9. But all we really care about is the fact that it's positive. So to the left, if we go slightly to the left, we get a positive first derivative. And if we go slightly to the right, and we plug in x equals -1 here, we get 1 minus 4 divided by -1 squared. That's 1 minus 4. That's -3. Again, we really only care about the sign, but we get a negative. So there you go. By the logic of the first derivative test, we've proved that, yes, this is a relative max because it has a positive slope slightly to the left, it has a negative slope slightly to the right, and has a slope of 0 at x equals -2. So yes, our answer before really was a relative max. And it would be kind of interesting, too, if they tweaked the problem a little bit. There we go. We've shown that k equals 4 causes us to have a relative maximum at x equals -2 like they wanted. But what if they changed the problem? What if they wanted us to get a relative maximum at x equals +2? Well, here, this is kind of the problem I was warning about. We would have to be very careful of this because there's only one value that we could choose that would make that a true statement, and that's still k equals 4. And by true statement, I mean the slope being 0. But remember, they wanted a relative maximum, not a relative minimum. Here, we would have a relative minimum. So if they tweaked the problem, actually, if they said that they wanted us to find the value of k, they gave us a relative maximum at x equals +2 rather than x equals -2. If you didn't do the last part that we just did, you would actually get it wrong because it would actually be a trick question. There would be no way to get a relative max at x equals 2. You could only get a relative minimum there. So that's why it's actually important to pay attention to that. So there you go. This is a good problem, I think, because it's a little bit more abstract than normal, and it's a little bit different from what you normally see, but that's how we work through it. If you have any questions, feel free to reach out to us in the comments. Otherwise, I'll see you next time.